This video is on conformations. Unlike double bonds, which are rigid and create a stereocenter, single bonds are free to rotate. Therefore, various shapes are possible. These shapes are called conformations. Have a look at these two structures and for a moment think about how they are different. Hopefully you will have noticed that the part on the left remained exactly the same in both structures, but the part on the right seems to be flipped. And we can really emphasize this with a new style of projection called a Newman projection, where we take a glance at the molecule looking at along a bond as opposed to the whole structure. The Newman projections really clarify the difference. As we can see here, on the left-hand side, the hydrogens seem to be overlapping each other. This would be called an eclipsed conformation. Whilst on the right, the hydrogens are clearly as far away from each other as possible. We would refer to this as staggered, and we would say it's a staggered conformation. The dihedral angle, or the angle between the hydrogens in this case, is at its maximum of 60 degrees, as opposed to with the eclipsed one, where the dihedral angle is 0. The staggered conformation is more stable than the eclipsed conformation as there is less torsional strain. We can see this if we compare the dihedral angles to the energy levels. We will notice that at eclipsed energy level, we have relative energy, which when rotated to 60 degrees, we end up with a dip in the energy equal to 12 kilojoules per mole, or 2.9 kcals per mole. As we continue rotating this at 60-degree intervals, we'll see an increase and decrease in the energy corresponding to that torsional strain. The energy is not very high, so free rotation about the single bond is ubiquitous, as in it constantly happens. Why is this? Because thermal energy at room temperature is 84 kilojoules per mole, i.e. that is how much energy there is just floating around us constantly. However, the lowest energy is still favored, so if we are drawing the lowest energy conformation, you should draw a staggered conformation. However, larger and bulkier a group is, the higher the torsional strain will be also. So we will see this in larger structures. Let's look at butane along the carbon-2, carbon-3 bond. And if we draw it like this, we start with the conformation where the two methyl groups are on opposite sides of each other. This is referred to as the anti-conformation. This is the lowest energy when the bulky groups are on opposite sides of each other. If we rotate it 60 degrees, we get an eclipsed structure, and if there's an increase in energy. And if we further rotate it 60 degrees, we get a decrease in energy again. However, we are not equal in energy to the anti-conformation. Why? Because the two bulky groups are next to each other. Yes, they are staggered, but because they are two bulky groups, they are still going to be interacting with each other. So we refer to this structure as gauche. As we further rotate it 60 degrees, the two bulky groups are now eclipsing each other. This is the highest energy conformation. We rotate it 60 degrees more, we end up with another gauche structure. Rotate it 60 degrees, we get an eclipse structure, and then finally another 60 degrees, we've rotated 360, we are back to the lowest energy conformation, which is the anti-conformation. Learn the terminology: anti, gauche, staggered, and eclipsed. Now it's your turn. Let's work with 2-methyl-butane. Draw the Newman projections and the energy versus dihedral angle plot about the C2-C3 bond. You may pause now and work on it. And here are the answers.